Hi, good evening. Thank the organizers and the speakers today and you for staying at that hour. So I'm presenting work that was done in Tel Aviv University by me and two doctors, Dr. Goran Gordon, who is an expert in active learning, if anyone interested, and Amir Natan. And I'm a material scientist. Material is completely different thing than data, different state of energy. But I'm going to take you for a journey to my field, and then I'll show you how deep learning works for my work. First of all, this is a bit about chemistry. The only thing that I'm talking about chemistry. The alchemy had a motto that ora, which means pray, lege, lege, re, lege, which means learn, learn, and then relearn, and then labora, which means works. So before we start working and talking about deep learning, we will learn a bit about computational physics and some stories about applications. But you probably can take it also to the learning things. So material science, all the materials that we have around, microelectronics, optics, electrochemistry, chemical reaction, drug discovery, everything that is based on atoms. Not high energy, but all the other physics that around us. And I started my PhD when the question was how can we improve the vehicles, the batteries for vehicles. One of the problems with the electrical cars is that the battery doesn't stay for long enough. So we have a bunch of materials that can help us to improve the batteries, but how do you choose your material? How do you know where to start and how would it work? So battery, just in general, this is a very short journey. There is a cathode and anode. Here it is an anode, here it is a cathode, and something in between. This is kind of capacitor. So probably for those who studied physics in school. And the electrolyte is kind of magic. Because you can put there whatever you want, which there are a lot of criteria why would it be good or not, and you have tens of materials to choose there. So how do we start? You can't search Google, you have to try your materials in the lab. But what can help you in real life is the computational experiment. Oops, sorry. I'll just run the movie. So what you see here is atoms running in computational experiment. This is the actual experiment that we did for oxygen within the electrolyte, traveling within the electrolyte. So if you want to do it in a lab, it will take like years of work. If you want to do it in computational experiment, you can't actually model this vessel, but you can model some hundreds or thousands of atoms. Depends on the resolution that you decide to work with. So a bit about computational experiment, because I'm a computational material scientist. So we have a lot of scales to learn about. If you talk about the wall system, it should be about millimeters, and it works for seconds or hours or more, even more. But this is the full battery. If you take a part of this battery, at the end we have some kind of, this is for example the cathode. This is an electron microscope picture of cathode. And here we have some microns, few microns probably. So on the cathode there is a chemical reaction that happens, and this is the reaction that gives us the energy for the battery. This is the reaction that receives the energy. So we need oxygen, we need lithium, and we need an electron, which should come to the same point at the cathode, and then we have energy for the battery. So what does it mean in the sense of our methods in computational chemistry? We have a lot of methods, but each method actually fits only for a specific scale. For example, we can treat by quantum level things that are at nanometers, few nanometers, and we can treat classically, atomistic classically, as you saw in the movie before, for nanometers or micrometers. And you also can, you have even more advanced method that can treat at larger scales things. But the problem with this method that you will not see chemical reactions there. And the chemical reaction is the most important thing for the energy, receiving energy from the battery. So if we can't model it, we can't model the vessel. Another problem with these methods is that as you go for a larger scale, you need more and more parameters that you need to fit somehow, probably from experiments, and that costs a lot of money, time, money, everything. So what we do in our experiment, we treat each atom as a point. It moves by, we know somehow what is the force that acts on it, and then we move it for some times. Then we have a lot of atoms moving. For example, here you can see probably a bit more atoms, but this is the electrolyte for another electrolyte, but without the oxygen. So the problem is, what is the force that acts on each atom? This is the main problem for me. How do I know what is the force that acts on each of atom? And then there are some classical models. This is probably something you know from static physics. Just two balls which are charged, they repel or attract or whatever. And so it's everything about the interaction. The interaction is actually a quantum thing, and then to know what is the interaction, this is about labeling. How do I label in my field? The interaction is something I want to label, and then I need to run a simulation. Quantum mechanical solution is a PDE equation, and then for many variables you have to solve it. It takes about 2 weeks on cluster for realistic systems that I show for you. Each point, I mean each data point takes 2 weeks on cluster, not on my PC. So it is pretty expensive thing. Just to explain you, when I need to know the diffusion constant, for example, I need 1,000,000 points. So this experiment is just not realistic for me, for now. But so here we come. We can say what do we want. We want a fast and accurate enough model for atomistic force. Atomistic force is the output of my model. We want it to be temperature transferable. I mean, if the system is heated up, the interaction shouldn't fall down, so it should be temperature transferable. And size scalable. What do I mean? I can get data for 100 atoms. I can get data for 1,000 atoms if I have a large cluster. but I can't get data for real vessel. I do want to simulate real vessels, so I can't get such solutions just from computational expense of it. So if I could learn from small systems, but apply it on large system, this would be good for our models. This is the main goal of my work. And another problem with deep learning, which you probably know, that it is mentioned, no one understands why does it works, and we try to see what can we learn about the physics from the model. Because the model is definitely not like your standard physical models where you do know what you do, you assume some kind of interaction. Here we don't assume anything. We just make this linear algebra, as you know, and does it actually learn some physics? So this was a question, and we try to answer it. So now let's go to work. What are the methods? So the general idea is that we learn, we make few thousands of quantum mechanical calculations through weeks calculations. And then we make learning, some learning for a long time, because the system actually doesn't change. As you saw, a lot of small movements doesn't actually change the interaction. But once in a while you have this quantum reaction. So you need to learn it again. Now you have new data, and you have to run more quantum mechanical calculations. So it takes some time, but then you learn again the space, your new part of space, and then you can work with the machine learning model. This machine learning model doesn't have to be deep learning. There are some CNN, there are some KRR methods, and even more. But I worked with the deep neural network. So the question for me was about what is the input. And you can treat it as an image, as a medical image that you heard before, but you have to remember that most of the matter is just empty. There are nothing there. There are no data there. So the data is only on the atoms. So what we do, we treat we take each time one atom. The output is the force that it feels, and the input is just the neighbors. And there is a physical theorem it's not a theorem, it's an axiom in quantum mechanics, that if you know the position, if you know the location of all the atoms and its type, just the type from the table, periodic table, you know everything about the system. So there is a model, there exists a model that can know everything about the system. Now you should just find this model. So we take this as input. The distances between atoms, this is the central atom that I'm interested in. This is its neighbor, and the neighbors actually define the surrounding. It's like a patch in a segmentation problem, probably. But a bit different because this is not an image. So this is the input. The model is pretty simple. It's completely same as you all know from standard courses. Yes?
What about the spin of the electron? Do you actually measure it too? Is it
what?
As well? The spin of the electron. If you, for example, do you measure a spin of particular atoms?
Okay, for my problems, I wasn't interested in magnetic properties or some spin-related properties. When you do labeling, you take it in account, so you can do it. I mean, you have the data. I didn't ask about the spin, I asked about the force, the classical mechanical force that it feels. But you can do it, then people do it. I mean, other works, yeah.
So also, what is the output that you are looking for?
I'm looking for forces, for atomic, each atom possesses some force. So this is the force, this is the vector with 3 components that I'm interested in. This is the fx, fy, fz, this is my output, and my input is just the position of neighbors. I decide about the number of few, let's decide about 10 neighbors, and this is the input.
Why 4n? Why 4n? N is the number of particles?
4 because I also included filter of 1 over distance. And this is because to make it with neural network take a lot, much larger networks, models. So, and I know that I need it from physical models. Yeah.
Are these arranged by something?
Yes, by the distance. Yes, it is important. So we have a model. We have training data. We optimize with usual methods. We use just standard Python libraries. And here is the results. So those are results from quantum mechanics. And those are results from our model. And you can see that they are pretty same. For pretty same forces. It's really small numbers here, and it's good enough for whatever properties that I'm interested in. So this was done for few different materials at different temperatures, and then we started to ask questions about transferability. So let us talk about temperature. What does it change when you increase the temperature of something, of solid? It becomes like softy, right? More soft. This means that the system becomes more amorphic and less ordered than at low temperature. So you can learn from a morphic system, for non-ordered system, to ordered system. But you don't expect the model to learn from ordered system to non-ordered system. So this is what we got when we started at large temperatures. When we learned our system with large temperature data, which means it was more amorphic. We got a good result for low temperatures. This is what you can see here. When you start working with when we teach your data on your model on the data of low temperature labels, then you can learn nothing. You can learn nothing. You can see these beautiful graphs that just have a large error.
How much is high temperature?
Okay, I use 2000 Kelvin, which means they are still kind of non-gas. All the materials, so they still kind of solid, and low temperature is room temperature.
So basically, when using a battery, like in my car or something like that, it's still the low temperature.
Yeah, sure. I can use this model for the battery. Yeah.
Excuse me. Just to make sure I understand what you show here is. Comparison of networks were trained on one temperature and tested on another, right?
Yeah.
So why don't you use the temperature as an input, as an external input to the network, so that it will be invariant in temperature?
You don't always. Okay. First of all, the temperature define the probability of the system to be in that and that position, state. It doesn't define, the positions do not define the temperature.
Of course. But somehow the temperature affects the
It affects the distribution of the states. They affect the distribution of the data. But you do have strange cold systems. They are rare. Okay.
Your systems, are you looking at things like phase transitions? Were you able to see something like this in this kind of phenomenon using this technique? Because I see most of these law graphs are just like...
Because there is no phase transition here.
It looks like very linear.
You don't have, no, this is the error, but I don't see phase transitions here. I would be interested in it, and this is like kind of further questions that we have, yes. But we have to make some proof of concept. These works are started in 2012 as medical science, and there are very few groups in the world that work on it. Last year it was Google group that started. So it is much slower than medical images development, and this is kind of first try.
So how much are you able to speed up the calculations using this technique?
So once I have a learned model, it takes less than a second on my PC, and then I can run million of. It makes possible to make real experiments. So the most interesting question for me was, can I learn from small systems to large one? This was the main challenge, because there is a limit that I can't go over it with the quantum mechanics, and I want to trust my model with larger systems. So this is what you see here is an errors that are shown for model learned from small systems and tested on large systems. Yeah.
How do you know large system data if you cannot compute it precisely?
No, here this is large systems that I could compute. This is the test.
Okay.
But look at the numbers. Here it's like 125 atoms. It is still small. But it is 4 times larger than this, and it takes, like instead of 2 days, 2 weeks, still it matters. Makes sense somehow. That I can trust the model to go into larger systems. So, and now what can we learn from this system? So what we try to understand is the parameterization. Well, how many inputs do I need? How many neighbors should I take in account when I build my model? And then we saw that for materials that has more nearest neighbors, we need more neighbors in the model. So somehow it understands at least that basic thing, that it's not clear exactly where it converges, how many neighbors do I need, but at this point, for example, for 12 numbers, 12 nearest neighbors for aluminum, this is the number of first nearest neighbors for aluminum, and it converges almost there. So it matters physically. Yeah.
Is this related to the crystal structure?
Yes, yes, it is. Although the systems that I trained on are amorphous, kind of amorphous, but it is related to crystal structure. Because the difference between the amorphous and crystal structure are somehow related also. So we have shown that there is sufficient accuracy that we can show with this kind of models in material science. We showed the larger system forces that we can predict. We predicted the lower temperature systems with the higher temperature systems, and we had we understood some physical insight from the parameterization. So then the grants, PASI and INREP Israeli grants, I have to, and you for staying yet, and questions.
If I'm not mistaken, you've shown that you needed to work on the learning model, then on this simulation, and then go back. And so I don't somewhere in
I know what this one.
This cycle. So I don't understand why you need to go back and forth with these computations. Why not?
Okay, I'll show you a realistic example of what I'm trying to do.
Yeah.
You have this battery. You start with oxygen in some kind of surrounding atoms. Then it goes to the cathode. Once it meets the cathode, I don't have the data for it.
So why wouldn't you run the simulation till?
If I know that it will go there, I can do it. But sometimes I don't want to do it because I want the system to find the path. This is you can say, why don't you just train your model on a large amount of systems, completely different systems, and then you find a different model, another than quantum mechanical model, and then you solve like the huge problem. There is a problem for calculation for quantum mechanics. If I can find a linear model to describe everything in physics, it's nice. But the problem is then you need a huge network. I don't want it. I want my network to be trained for my particular system each time, and then it becomes very small and nice to work. But people do also what you suggested. Yeah.
So were you able to, for example, build these kinds of batteries, understand that's what your research is, and then compare them to the actual theoretical prediction? Is this part of because I understand that you're doing comparing simulation with simulation.
Yes.
Were you also comparing physical system?
Okay, yes. When you saw this, I didn't, yes, we want to, but first of all, we know the error of the theoretical model. We know the precision of it. And then, if you look here, this is a radial distribution function. Where are the neighbors distribution? And the black one is for the crystal of alumina, which is really related to the experimental one. The red one and the blue one are for different temperatures with the simulation. But you can see that the peaks are at the same places, and this is the relationship between the different temperatures. But we didn't compare directly to experiment yet. But it would be interesting, of course.
So is it matching some theoretical statistical mechanics?
Yes, the idea is to solve statistical mechanics problems, such as finding diffusion constant, finding phase transitions, finding this kind of stuff. So then you need statistics, and then you need millions of states to average over millions of states to find these properties. That's why I need the force.
Yeah, so that's a tool that you will use for that,
Yeah.
but it's not yet shown.
No.
Okay.
No, not yet.
The direction.
Yes, but exactly. And there are some works that are very close to that. Okay, thank you.